right, here's a picture of a Air Force T-38 that we captured with sonic booms a couple of years ago. If you look at this picture, it kind of looks like a boat on the water, right? So you've got a lot of the wakes here. So what a sonic boom is the pushing, it's traveling faster than the air is able to get aside. Not different than a boat wake. So you could fly slow enough, or you could, on the water, you could travel slow enough that you don't create wakes. Once you go fast enough, you would create wakes in the water, and you get the same thing in the air, except in 2 dimensions, it's in 3 dimensions. So here's some other pictures. So here's our 3-dimensional. You've got shock waves coming off in a cone shape and not just off to the side like you would on a boat. So here's a T-38 from above. Here's one from the side. And I'll talk a little bit more about some of these pictures here in a second. One interesting thing, some people may think that you only get shock waves when you're breaking the speed of sound. That's not true. You get shock waves as you are continually flying above the speed of sound. What we have here is the carpet that we're developing when we're going supersonic. So this is a good illustration of the carpet going across the ground, following the aircraft. When they pass a person on the ground, that person is going to hear the shock wave. That's why you'll hear a shock wave over a wide area, but not at the same time. It's going to flow through the area. All right, let's talk a little bit about those shock waves and what's happening and how they get to the ground. So this is a real picture of a T-38. Notice you'll have many shock waves coming off the aircraft as the area of the aircraft gets larger, a shock wave develops. So you can see there's probably around 12 to 15 shock waves right near the aircraft. As they travel down toward the ground, these shock waves coalesce or group together. So right here we're seeing maybe 3 or 4 shock waves. So similar to what we're seeing here, that same thing happens to the point where the shock waves only develop into 2 when they hit the ground from a higher altitude. What we have here is the change in pressure over time. So that change in pressure is related to an acoustic or sound level. So that's where you're getting the quick, sharp change in pressure once and then again on the back end, and that's that boom, boom that you hear. One other thing to point out when we talk about N waves, you'll notice this pattern kind of looks like an N. So that's why we call it an N wave signature for our current supersonic planes that are flying around. All right, let's talk a little bit more about an N wave and then what we can do in the future to reduce the sound level. So this is the pressure change over time, like we described the N wave with a boom, boom. This short little time from here to here, basically between these 2 points, is called the rise time. That's the amount of time it takes to go from regular pressure level or standard atmosphere level up to the boom, the change in pressure for the boom. And that is your pressure change, okay? What we try to do is increase this rise time, so make it longer, and then decrease this pressure level to something less. And that's how we will attack making the boom less loud. So it's important to understand that as we look at some of the waves that we're going to capture today and during this week. All right, for this kind of test, we have an F-18 that's flying up to 32,000 feet. It's got all these shock waves coming off the plane. As it works its way down, the shock waves coalesce into 2. Here's that boundary layer we're talking about. We're typically seeing it between about 3,000 and 6,000 feet is the start of this layer. Our TG-14 motor glider we have flying right above it to capture these shock waves here just above the turbulent layer. And then down at the bottom, we're not going to see a pure N wave, as I'll show you in a second. You'll see some spikiness and some reduction, which is what the turbulent layer is doing to the boom. All right, so this is actual data. This is an N wave, as we discussed before, from the TG-14 up above the turbulent layer. So it kind of looks like an N. Now here's a wave we recorded on the ground. So it looks generally like an N, but you can see a lot more spikiness in these areas. And that's created by the turbulence on the ground. When this pressure goes up higher, that's going to be louder, the spiking. If it gets cut off the top and gets lowered, that's going to make it less loud. To better understand this is an analogy that's pretty decent to understand the basics. It's not exactly the same characteristics. But if you can imagine a pool, so you've got a pool rippling on top, you can see that there's areas of light where it's really light, and then there's areas that are darker. The lighter areas would be similar to a louder boom. The darker areas would be a softer boom. So this is a good way of representing an entire area over the ground, and why it's so hard to measure this, and why we need to fly so much. So in order to characterize this, we're measuring one location of how turbulent it is overall, and then we're recording booms across an array through here, and then that array is going to see different levels of pressure. So we need to do a lot of boom recordings on the ground and a lot of flights. So statistically, we can figure out how much that boom varies with different turbulence levels. Okay, on to the flight research that we're conducting here. One of the things we're trying to do is validate our code or our models that tell us how the sonic boom propagates through a turbulent atmosphere and how much it can change. We're going to use these actual test flight results to go back to the computer code and make sure it's correct. And then we'll use that to predict the loudness of low boom designs that we have in the future. And yes, this is called Sonic BAT, for sonic booms in atmospheric turbulence. Before we came out here, though, last summer we were out at our home base at Armstrong Flight Research Center on Edwards Air Force Base. Here's a picture of what it looks like with the dry lake bed, and Armstrong is right in this area. So what we tried to do there is to record data in a hot, dry environment with varying levels of signatures. We used an F-18 to generate the booms. We had 3 microphone arrays on the ground and to record the booms on the ground. We used a TG-14 motor glider to record the booms above that turbulent layer, and what we would do is turn the engine off so it's pretty quiet flying, record the booms, and once we heard the boom, we'll turn the engine back on and climb up to the altitude. So that's a great plane to do that kind of activity. We also recorded a lot of different weather data to characterize how that atmosphere at low altitude was turbulent. For us, it was just over a year ago, about 10 days of flying between July 11th and the 22nd of 2016. We flew 20 flights and had 64 sonic boom passes during that time. We utilized 2 F-18s, just like we're doing here, and a TG-14. Interestingly enough, that TG-14 flies about 100 miles an hour, and we've taken 5 days of flights to get it out here instead of taking it apart, which probably would have taken a month. So it'll be you'll probably get to see it today. You can see this is the team. We have a similar sized team here for this particular round. All right, so here's some results from that test as we talked about before. So once again, this is the pressure change over time, and what you're really seeing here is each one of these colors is a different microphone spaced at 100-foot spacing. If you look at this sort of run, the average peak pressure should be right here, 1.6 pounds per square feet. So you're seeing a lot of spiking here. And before I talk any more, pounds per square feet is not a number that a lot of people are used to, but you probably know PSI, or pounds per square inch. 1.6 pounds per square foot is approximately 0.01 PSI. So it's a very, very small pressure change. If you look at your tire pressure being about 30 PSI, we're looking at 0.01 change on these pressures here. We also found areas where the shock waves were a little bit less loud. This is the rounding that we're talking about, and that reduced the loudness of the shock waves. And I forget, Ed Herring, our principal investigator, always likes to say, this amount of pressure change is about 2 flights of stairs. But it happens so quick, that's why you get the loudness. Okay, now moving on to what we're doing here. So we're flying out of the shuttle landing facility here at KSC. In fact, we are in this location right here in the ops building. We're going to record a similar data set that we recorded out at Edwards, except we want to be in a humid climate. Humidity has an impact on shock waves and also on the turbulence, so we want to see the difference between what we recorded at Edwards Air Force Base and what we've got here. Our approach is the same. We're going to have 2 microphone arrays rather than 3, and we've added some new weather equipment that's going to help characterize the humidity in addition to the turbulence. We're kind of in the middle of the flights right now. We planned 2 weeks, 10 days of flights with some backup flights in case there's weather or hurricanes or maintenance issues with the aircraft. So far we're doing really well in getting our flights done. We're trying to fly between, the booms occurring between 10 a.m. and 9 p.m. We already had a flight at 8:30 on Monday. We may have another one as early as that later on, but we're still determining that. Oops. We're looking for a minimum of 33 booms, but we want to see different turbulent levels. We want to look at a high, a low, and a medium turbulence level. So even though we reach 33 booms early, we might not have the right mix. And right now we are not finding a lot of high turbulence areas, so we might have to extend past those numbers of booms in order to get that. We have 2 F-18s and a TG motor glider, and like I said, we're flying from this facility right here. All right, so the boom footprint. We have a program that is based on the aircraft speeds, altitudes, and the weather from where the aircraft is flying down to the surface. We can figure out what the boom footprint looks like. These are all different pressure levels here. So based on this sort of picture that we calculate each day, based on forecast winds and temperature and other weather, we're trying to keep the boom foot off of the Titusville and the other cities along the coast. What we did is took this footprint, and that's their main area of booms, and just in case there's changes in forecast, we added a little buffer zone to make people aware that they could hear booms in that area. And it sounds like some of that is happening. We are getting a few booms in Titusville, but once again, we're trying to keep that off based on the daily weather in that day. Okay, as far as what we have on the ground here, we're in the ops building at near this hangar. We're going to go out to the center of the airfield where there's a big shuttle mock-up and the tower. Just to the east of that, we have a microphone array, 1,500 feet long, 16 mics, 100-foot spacing. We have some weather equipment and weather balloons here. And then we have another array a little bit farther off, same sort of microphones, 16 microphones, about 1,500 feet long. So that's basically the setup. And then we have a command and control vehicle that Kennedy has let us use, so we can have good radio comms with the pilots. I'm not going to go through all these individual pieces of equipment, but there are a lot of different weather equipment, a lot of wind measurement, temperature measurement, and heat flux measurement that we have to capture so we know how turbulent it is. We also are sending up a weather balloon for each flight, so we're characterizing the atmosphere from the surface up above the flight profile of the F-18. All right, moving on to today's flight. A better close-up of the TG-14 and one of our F-18s. And like I said, you'll be able to have a chance to see this later on, up close and personal. All right, so after this briefing, we'll start heading out to the midfield press site around 10:30. We'll have the TG-14 take off at 10:45. We do that early so we can get up to altitude and set up while the F-18 can climb much faster up higher. And we'll be ready for the F-18 takeoff at 11. Expect that we'll get 3 sonic booms between about 11:20 and 11:35. We see that it takes 6 to 8 minutes per pass to hear each boom. After that, there'll be a low flyover of the F-18 as it returns here. We're going to let it go down to the visitor complex, so we'll fly over the visitor complex, and then it'll come back and land. After that happens, we're going to invite you to come back to this hangar. Once the aircraft shuts down, you'll be able to talk to a few of the subject matter experts and the pilots of both aircraft. And at about 13:30 or so, we expect that we'll let you leave the shuttle facility beyond your day. So if we were a little bit worried about weather, but our forecast this morning looks pretty good. And so I think we're going to have a good mission today based on the forecast. All right, some of the things to look for. So the TG-14 is going to look like this, a little piece of white in the sky. I'll try to point it out if I see it out there. We had a pretty good luck yesterday, and it's going to be at about 4,500 feet to 5,000 feet. So we should have a chance to see it. F-18s are a little bit tougher to see, but once it's up at 40,000 feet, it's going to start it to be able to accelerate as it is in its dive, we might see some contrails. Once it dives from 40,000 feet, they'll kind of disappear. We'll also have a chance to see it when it climbs back up after the pass. We're going to do a quick climb up to 40,000 feet, and we might see the contrails. So I'll point that out for you as we're out in the area as well. Yesterday we were able to see it at those 2 times. I'll also have a radio, so we'll hear the pilots talking to our ground controllers. And I've got some speakers, so feel free to listen in on that. Here are the calls that they're going to make. They make a turning in call. That means that they're, get ready, people on the ground. I'm starting to make my way in and set myself up for the run. There's a 2-minute call, and why does 2 minutes not match 3 minutes of boom? There's a point in the sky that we tell the pilots to fly to, and that point is going to allow the boom to travel from there down to the ground to our microphones. Right now the time is about 1 minute from the mark call that we're going to have to the boom on the ground. So if you hear 2 minutes, it's going to be about 3 minutes of boom. 1 minute is about 2 minutes of boom. You'll hear 30 seconds, 3, 2, 1 mark. And Ed, do you happen to know what the propagation time
I
is?
look it up, it's like 75 seconds, probably the exact number.
Might be a little bit longer than 1 minute, so that was a rough time. We'll let you know that out there, and Ed's done a pretty good job of marking the time and saying the boom will be in 3, 2, 1, and within a second, you should be able to hear it at the site. You should hear that big double boom. If you, I hope you've heard them before. If you haven't, it is a little startling. And people will be jumping, but we're getting good data on the ground. We'll hear the aircraft parameters, how fast it's flying, how much fuel it has remaining, so we have an understanding of how many more passes we can do. And I already talked about the time between booms. And then I talked about the flyby, if people have it again. Okay, so that's what's happening today, but what's happening next? We do have a model on the table of this demonstrator. So NASA is building a low boom flight demonstration X-plane. We just were approved with it, and we'll talk a little bit more about what it's about. But before we go there, there was a ban from the FAA on supersonic flight from Concorde and the proposed supersonic transport back in the early 70s. So since 1973, both the FAA and the International Civil Aviation Organization, which is the international version of the FAA, have banned supersonic overland flight. You can do it over water, but not over land. We believe at NASA that the standard should not be a speed standard, but should be a sound standard, just like everything else. So we are working towards helping provide data to these organizations to set the standard. So why do we want to fly supersonic versus flying our 0.9, 0.85 Mach flights we currently have in airliners? Well, in some cases we can get to places about twice as fast. And for those that travel, that is a huge difference. Do I really want to spend the whole day going out to California, or if I can travel out there and be back in the same day, you might be more than likely to do that. So it's valuable to a lot of people in the U.S. It is also an opportunity for the U.S. to continue the lead in the aviation industry and not let another country take over. That's one of the few places where we are still in the lead. We believe there is a large market potential for both business type aircraft and civil airliners if we can make the sound, the right sound level for these booms. And like I said, there's a huge impact that it could have in the U.S. Also, while we're working on our research, there are a lot of companies that have or are continuing to do research in supersonic flight. Most of these are not low boom, but they are learning how to go supersonic, and that's part of what they're trying to do in the future. But if we can set a standard, I think a lot of these companies will jump in and they will start designing to that sound standard. But no one is willing to start designing to a sound standard that may not be allowed in the future. So why a demonstration? One of the things the FAA and the ICAO want us to do is collect data in communities and see how annoyed people are at different sound levels. We don't have a plane that's low sounding enough with sonic booms right now. So in order to get that sound level, we're building a plane that can be at a pretty low sound level, and we can increase it and figure out what the annoyance level is for each different loudness level. Once we collect that, we will give that data to the and they will decide based on our numbers what they think we can accept. And it'll be we're not a regulation organization, we're a data organization, but we have been working with the FAA and we will be providing that. We do have a neat maneuver that we learned in California. I think Ed Herring, once again, found this and started this. If we do a rollover dive with an F-18 over a small area, we can get a low sounding boom. It's not a shake boom like I talked about, but a lower amplitude in wave. And based on that, we have in the past done some community response in areas that are custom to sonic booms. But this is something else we might try again this next year in one of the areas over the US. That's all leading up to using the low boom flight demonstrator in the future as a way to gather data. Okay. So one of the things I was talking about is how to measure response. So if you think about the in wave we had before, this wave is much lower in amplitude and it has a longer rise time. So the sound level coming off of a future plane is going to be much less. We have shaped parts of a plane before, but you're only seeing part of the sound level. The rest of the plane is still loud, so we really can't use those types of planes to get this data. You need a nose-to-tail aircraft that is low boom. We also need to conduct this over many communities. We're looking at 4 to 6 in the future. And as we said, this requires a research platform. So a better look at what I was talking about before. Here's where the Concorde was at 2 pounds per square foot. We're looking at much less and a shorter rise time. So what this plane should be capable of doing is if you were having a normal conversation, you might not even notice a boom happening outside. If it's really quiet, you'll hear something, but it's not going to be like the booms you're hearing today, for sure. Okay, so where are we on the low boom flight demonstration? Lockheed Martin was contracted to develop a preliminary design. This has been called QUEST, Quiet Supersonic Technology. In the future, it's going to go back to being called low boom flight demonstration. The preliminary design review was held in June. This contract should be over in the not too distant future. And we released a request for proposal to other companies to do the final design, manufacture, and test of the aircraft. The timeline for this, and remember these dates are all subject on funding and not having any slips due to technology or other reasons. But we expect the design and build contract to be awarded next year. Our first flight will be in 2021. We're going to do some work out at Edwards or Armstrong Flight Research Center in 2022 to understand if the acoustic signature is what we predict. And then we expect to fly out of that location on an initial community response test. Following those tests, we expect over the next 3 years to take them around the country, looking at 2 to 3 communities per year. All right, so how does Sonic Bat go back to the low boom flight demonstrator? I think I alluded to it, but we have a pretty good idea how booms are modeled minus turbulence for the low boom flight demonstrator. This is one of the first tests where we've measured booms and turbulence, but also measured really good weather data so we can kind of correlate those. So using that, we can build a model for in-wave type aircraft or the current aircraft. Then we'll use the same model to propagate the low boom signature that we have in the future. And then once we get the low boom flight demonstration flying later on, during that acoustic testing in 2021, 2022, we'll compare it against that and make sure our model matches what we're seeing on the low boom flight demonstration.
We've done it in dry air, but we needed to get some humid air, so we're down here, playing here in Kennedy. You guys are maybe not quite as used to sonic booms as they are out there at Edwards, but you've had your share with the shuttle and some of the other rockets that have come back in here, so we figured this was as good as a place as any to go and try this kind of machine.
Colonel, can you describe your dive, when you're at 40,000 and you dive into creating the boom?
Yeah, so the maneuver that we typically will do is we go outbound to about 30 miles and turn in, and we're about 0.9 Mach, 40,000 feet. When we get to about 25 to 28 miles, depending on how heavier we are, the further out we start the dive. We go to about 10 degrees nose low, full afterburner, and quickly accelerate through Mach 1. And then we level off at 32,000 feet. Usually when we level off, we're probably somewhere right around Mach 1.2. Sometimes a little more, sometimes a little less. We continue the acceleration up to Mach 1.35, then we kind of hold that until we hit the point. Then as soon as we're done, we give it a couple of potatoes, then we start a climbing turn, so it will do what we call defocus the boom out in front of us, so that Cocoa Beach doesn't get blasted, and then turn to the downwind and go back out and do it again.
What's it feel like inside? Can you describe the G-force and what's it feel like when you're doing that maneuver?
Sure. The biggest thing is you're busy. You really don't notice that you've gone Mach 1 other than the HUD says Mach 1.00. So you really don't notice when you go supersonic. If I was level, I'd probably see the altimeter jump back and forth a little bit if I was doing a level acceleration. But then once you're above about Mach 1.15, the altimeter kind of mellows out again and gives you a good accurate reading. But you really don't notice anything. There's really not much G-force involved when you're doing it. But the biggest thing is just because you're moving so fast, things are happening a lot faster than going 55 down the freeway.
So you're going supersonic. So does anything change with your equipment? I imagine you have earphones on, or does anything change with the sound once you hit that barrier that you notice?
That's a good question. Some people ask that all the time. What do you hear in the cockpit when you go supersonic? And I don't hear anything. So in the cockpit, you don't notice it at all. Part of it is the rapid change that you get. So for me, nothing's really changing that rapidly. Even when we go and probe another airplane, so we'll look at what the shocks right next to the airplane look like, and we'll be in another F-18, say probing an F-18. As we move in and out of the shocks, you don't hear any. You will feel the shocks. They will push the airplane around. Like you don't feel, like I said, you feel stuff, you don't hear anything.
How do they push the plane around?
Well, what you get is because it's a pressure change, so it's pushing on, say, one wing and not on the other wing. So essentially, it'll kind of move you back and forth a little bit, or maybe it's pushing on the nose but not on the tail, so it might push the nose down, push the tail down, or something like that.
Like a little bit of turbulence.
Yeah. Okay. And it's a little bit of turbulence, but almost more like a hand pushing on it, like somebody going out and pushing on the wing or pushing on the nose. So, and it's not real fast or anything like that, so you can compensate.
Do you ever see things like, do you ever see the cloud kind of develop along your wings or along your nose or anything like that?
No, but you can sometimes see the shock, believe it or not. If you're probing an airplane, you can sometimes, depending on the atmospheric condition, it looks like a clear line. Other times that you can see it, if the sun is in the right place and I look out on the wingtip, I'll actually be able to see the shadow of the shock wave. And as I go faster, the Mach cone, it gets more acute or more angular, if you will. And it'll move back, and you can actually watch that, as you speed up, you'll look out there and see it moving back on the airplane.
Are you more likely to see it if it's humid, or?
That's a good question. I actually don't know.
Okay.
So I should ask our guys whether they know.
So why is this important? Why is all this testing important? What's the practical applications of this?
Well, we'd like to be able to, I want all you guys to be able to go supersonic too, and not just to go supersonic. It'd be really nice to be able to get to New York in half the time, that it takes now. So one of the ways you got to do this is you got to figure out a way to get that boom shaped or lower in amplitude. So there's a lot of different things you got to look at, and one is the shape of the airplane, but the other is how does that shock wave move through the atmosphere? And one of the things that we're looking at with this is how does turbulence affect that shock wave, and can we use that to predict what's going to happen to the shock wave so that we can look at it in all kinds of different areas, regimes, problems to make sure that it's not going to be a problem if you're trying to get from, say, Orlando to New York in half the time, or Orlando to LA in half the time.
The plane of the future that limits the amount of shockwave and sonic booms, what kind of plane does that look like?
When they banned those lawn dart things that used to throw in a circle, if you're old like me, you remember those? So it looks a lot like a lawn dart. It's a long, skinny nose. They have to really plan the lift distribution. If you look at the low boom demonstrator pictures that are out there, the cockpit is about halfway back. So I'm going to be a good ways back there. The other thing you'll notice is there's hardly any bumps on it. Really long nose, and you can't see out the front of it. So one of the things that they're looking at is high definition television cameras, much like what are around me now, and then also a screen in the cockpit that I'm going to fly off of that I can use to find other airplanes when they're down low and take off and land it.
As a pilot job, how cool is being a test pilot for NASA? How does that rank in the?
Well, being a test pilot's what I always wanted to do. I mean, I decided at age 16 when my high school science teacher handed me a book and said, "Here, read this." And I said, "Why?" He said, "Just read it." And the book was the right stuff. I couldn't put the book down, and I said, "That's what I want to do. I want to be a test pilot, maybe have a shot at being an astronaut." So I then said, "Well, what do you got to do this?" Well, I figured I was going to be an engineer, so okay, engineering degree. Probably need to join the military if I want to fly the things that go fast to do this kind of stuff. So ended up going to the Air Force Academy, getting an engineering degree there, and going off to pilot training, and just kept plodding along until they sent me to test pilot school. And one of the interesting things is, from the day the guy handed me the book to the day I actually finally got to do a test like what I read in that book, it was probably about 15 to 17 years. So sometimes you think and go, wow, that seems like a long time, but the good thing was it was a lot of fun along the way. So getting to be a pilot, my friends at the Air Force Academy are some of the best friends I have that are out there. So it wasn't like I was just slogging along studying 24 hours a day to get here. It was a great path, and once I got here, it's everything that I thought it would be.
This is part of understanding how that boom sounds when it reaches the ground based on different weather conditions.
And how did the test go today?
As far as we can tell, the test went very well. He successfully got 3 passes, which is about all we get before we've run the F-18 out of gas. He's using a lot of gas and afterburner, getting up to Mach 1.35. We had good weather conditions, probably moderate turbulence, which is one of the things we're definitely looking for. And as far as I know, all the arrays captured the data. So now the scientists will spend probably months looking it over, trying to figure out what it all means and trying to learn from it.
And why do the test here and other places?
Okay, so we're here in Florida to get definitely humid conditions. Out at Edwards Air Force Base in Southern California, where we normally operate, we've got a lot of hot and dry conditions, but we don't have the humidity that you see here in Florida. We don't have clouds intervening between the aircraft and the ground, and we definitely don't have the humidity.
Can you tell us who was flying it?
I'm sorry, who was
Can you
flying?
tell us who was flying it?
Yeah, the F-18 today was flown by Tim Williams, and the TG-14 was flown by Dean Neely and Sam Cantor. He's the engineer operating the instrumentation system in the TG-14.
Then can you explain to us how this ties off with Edwards Air Force Base, why you did it there, and then why you're doing it here, and then where you might go from here?
Sure. We do most of our testing out at Edwards Air Force Base. That's where the Armstrong Flight Research Center is located. That's where we have our F-18. So that's home for us, and that's where we do most of our testing. But as we started to gather a lot of data under those very specific conditions, generally hot and dry, the scientists started to wonder how different weather patterns would affect things. Any kind of future transport is going to be flying all over the country with different conditions, and there's a whole half of the country here that is represented by Florida that we weren't getting that data out at Edwards.
Can you explain the process, why you had the 2 planes, what the glider was doing, how that whole process went on up there?
Okay, so again, the F-18's up at altitude. He's just making the sonic boom. The motor glider goes up, and they try to figure out where the top of the turbulence is. You can basically feel that as you're climbing through it. They want to be above the turbulence by maybe 1,000 feet or so. They will park there. Well, not park, but they're flying, they're gliding. Because it's a motor glider, they can actually shut the engine off about a minute before the boom is expected to pass through, so everything's very quiet. They have a microphone on the motor glider, and they measure that boom before it hits the turbulence and passes to the ground. So we've got the kind of the undisturbed shock wave, and then the ground array gets it after passing through the turbulence layer. If You subtract the difference between the two, now you can figure out what effect the turbulence had on the sonic boom. So I think after this, the scientists will definitely be looking at whether there's other locations, other weather conditions we might want to consider. We've hit the gamut of dry and humid. I'm not sure whether cold is a factor in this or not. It takes a unique location where we're able to find restricted airspace we can go supersonic legally, and then have an area on the ground where the scientists can set up the array. And Kennedy Space Center worked out very nicely for that because we can fly off the coast in the airspace there. NASA owns the ground facilities here and was able to set us up for the ground array. So we'd have to find another location that meets all those requirements.
What is the next step after this? When you get this data, analyze this data, eventually we want to actually have the impact. So what's the next step and when are we going to have an impact?
Okay, so this data will feed into a display that we're working on developing that will provide the pilot in the cockpit an indication of what his boom is doing real time, so that he can then avoid population centers if the weather conditions are causing it to be louder than expected on the ground.
But you actually don't you want to change the technology on the airplanes itself, right?
That, yes, we do.
That's what I want to know
Okay,
about.
so the next program related to this, but not a direct follow-on, is the low boom flight demonstrator. That is a purpose-built X-plane we're hoping to fly in a few years that is actually going to shape the aircraft so that the boom is a lot quieter. The F-18 that you heard today, that is just a normal sonic boom off an F-18. Nothing was done to make that quiet. The next aircraft we're going to build is going to try to demonstrate that you can quiet that boom, and then if you know the weather conditions and can alter your flight plan, the hope is that nobody on the ground will even know that you're flying overhead supersonic.
That plane could change its curvature in flight, is that right? That's the goal?
No, that is just specially shaped from the
beginning.
outset to
Okay.
have a much quieter sonic boom. And so it will not change its shape in flight.
And is that the next X plane, that X 40 something?
Well, it doesn't have a number yet.
Oh, it doesn't.
It doesn't have a number yet. Once they start building it, then it will be assigned a number.
Okay, thank
We
you.
do have an X-57, which is an electric airplane. It has nothing to do with supersonics.
Yeah.
So this is a piece of